Hello, everybody. Thank you for joining us. Today, I'd like to provide an overview of an introduction to using machine learning on a small microcontroller. So we'll have a look at the key machine learning algorithms that we can run on a microcontroller, the sort of hardware support that's now available within the Cortex-M processor family, the additional design tools that we're going to need to design our machine learning algorithms, and also the methodology that we need to use to go from a machine learning algorithm and porting it down onto a small microcontroller. Although we're providing an overview today, we'll be running a series of webinars which go into more detail through July. So these will expand on what we cover today and also provide you with some practical examples that you can use yourself and experiment with and get an initial understanding of how to use machine learning algorithms down on a small micro. So some of the advantages of introducing algorithms directly onto a microcontroller, particularly within an IoT device, is that if we run the machine learning inference on a small microcontroller, then we only need to transmit the result of that inference rather than a large amount of data up to a cloud computer for it to run the inference. So we're cutting down the amount of bandwidth that we need. Running our inference locally also reduces the latency, so it's just going to be much faster than transferring data up to the cloud, running the inference and getting the reply back. Also reliability, so the device can run standalone so that we're not dependent on having a big cloud and IP structure. This also makes our end design much more economic to run as well, that we don't have to maintain a big cloud infrastructure for 10, 15, 20 years. And we also have an important privacy issue that all of the data is held on the device and it isn't ever shifted out of the device and onto the cloud. So there's a lot of strong advantages to using machine learning algorithms on the microcontroller. The sort of uses that we can have, basically we can do object detection, tracking, we can classify images, we can integrate our machine learning algorithms into a control system. We can use it also for monitoring, so anomaly detection is also a very good use case for machine learning algorithms. We can create new styles of user interfaces, so spoken words, so keyword spotting, gesture detection, and we can also transform signals and clean signals up as well. So there's a whole range of uses that we can put these algorithms to. Now, in terms of support within the Cortex family, the Siemsys DSP library does now provide some what's called classical machine learning algorithms. So these are things like support vector machines, Gaussian Bayes inference, and also distance functions that we can use within clustering algorithms. Now these we'll discuss at a later date, but today I want to look at the neural net support and also support for convolutional neural nets that's included within Siemsys neural net. So this can either support neural net algorithms with a purely in software, or with our newer microcontrollers, they might be fitted with the ARM Ethos neural processing unit, and ARM also provide a plug-and-play driver for their neural processing coprocessor as well. So when we come to develop a machine learning algorithm to run on a small microcontroller, we have quite a few moving parts to consider. So getting this up and running and a good design flow is kind of the initial stage of our project. So here, everything in orange is basically done either on your PC or within a cloud computer, typically using Python scripting language. So first of all, we have to have a block of data that we're going to use to train our algorithm. And very often this has to be labeled data. So again, this can be quite expensive and time consuming to process, but we'll look at some shortcuts to this later on. We then have to design and train our machine learning algorithm. And this is typically again done within the Python scripting language using a library language called Keras as well that we'll have a look at later on. Keras provides an interface to an underlying library called TensorFlow, which will actually produce our machine learning algorithm. So we can design and then we can go through and test our machine learning algorithm within the Python environment to check that it's meeting the accuracy that we need. And once we've achieved a good model, we can then convert this to TensorFlow Lite so that it's able to run on a small microcontroller. This is basically reducing the number of operations that are required to run our model. And this model by default is in floating point, so then we can quantize it to take it down to 8-bit variables. And again, this will greatly reduce the amount of memory that we need on a small microcontroller. Typically, we'll again test it to prove that we haven't lost too much accuracy over the floating point model. So when we're happy with that, we can then export the model so that we can run it on a TensorFlow interpreter that we have on the microcontroller. So this export typically then is a header file that we simply add to our project. And once we've got the inference running on our microcontroller, we'll probably still want to acquire data and stream that back so that we can go around the whole loop a number of times. So once we've deployed our initial machine learning algorithm, we'll still be acquiring data to retrain it and improve it over time. Okay, and this is quite an important point, so that we have another loop where we're training, versioning, deploying it over the air, adding it to our device and streaming out more data into a large data store and continually going around this loop until we've trained our algorithm to a very high level of accuracy. So this, again, these stages is something that you would need to consider at the beginning of a project, typically how you're going to acquire the data, how we're going to deploy and update the model. So in terms of our development tools, as I've mentioned, typically we're developing the model code within Python. And within Python, we need to import a number of packages. So TensorFlow at the moment is probably about the dominant machine learning platform. This was developed by Google and then released open source, so it's free to download and use. Sitting on top of that, we have a language called Keras, which allows us to define the TensorFlow model. And then we have a number of other applications that we can use to acquire and clean the data. TensorFlow also uses a matrix library called NumPy, so for all of its tensor operations. Very often we'll also need to visualize our data and training information. So again, we use a graphical package so that we can plot library data. And there's also a useful tool called Netron so that we can plot out the TensorFlow graphs, so the layers of our machine learning algorithm. So we can see exactly how those have been implemented by TensorFlow. The sort of development environment that we need to use, the most frequently used one for machine learning applications is a thing called Jupyter Notebooks. So this gives us a sort of word processor type environment where we can create cells, and these can either be pure text cells as shown at the top of the screen where we can write a description of what we're doing within our model. And then we can have active code cells where we can put in our C code and then we can run the code in that cell. So we can write small elements of code And then as we go along, we can run those step by step and actually see how things are progressing, modify it, and go back and round the loop repeatedly. So Jupyter notebooks are very, very good and ideal for developing machine learning algorithms. We can run those locally within a data science package that, again, is free to download called Autoencoder. So this sets up an environment on your PC. Or we can go on to Google Colab, and that provides a complete machine learning environment with Jupyter books to use straight away. And behind that is a cloud computer with the option to do all of your training on GPUs as well. And this is all free to use. So generally, I tend to use Colab, but I've also had Autoencoder installed on my laptop as well. As we are developing our machine learning model, there's a lot of experimentation involved. So you'll define the model, you'll train it, and then you go around that loop a number of times, tweaking various factors until you get a model that you're happy with. So it's very important to keep a record of this experimentation. And within the Colab environment, there is a thing called TensorBoard. So this allows you to keep track of all of your experiments, and you can compare different features side by side as graphs within TensorBoard. There's another service called MLflow. So this is a standalone website which allows you, again, to record all of your experiments and store all of your assets for your different machine learning projects. So these are worth investigating at the beginning, because as you get deeper into the project, you need to be quite methodical about how you're developing and changing your model, so you keep records and kind of improve things in a sensible way. There's also another company called Edge Impulse, and they provide a set of automated tools that help you create a model and train it for common use cases. Again, this is free to use for small teams, and it gives you a certain amount of runtime on their computer. But they also have a tuner as well, so you can define your model, and then sort of probably a neural net in its own right will go in and train your model and do all the tweaking for you. So after you've sort of played around manually, it's all very exciting to begin with, but very soon it becomes quite boring because you're going around this loop endlessly. So investigating Edge Impulse is worth doing, because it will take a lot of the drudgery out of preparing your machine learning model. Again, it has some very good tutorials and wizards, so you can just go onto the website and you can have a running keyword spotting model in 10, 15, 20 minutes. As I mentioned, within the microcontroller, we have machine learning support within CMSIS DSP. There's a separate CMSIS neural net that provides the low-level primitives for Cortex-M devices. Also available as software packs is the TensorFlow-like micro interpreter, so that we can easily add that to our project as well. Another very good way of developing and testing the machine learning model is using the ARM virtual hardware simulation models. So these typically will model a Cortex-M55 with the neural processing unit, so that we can build our code and then download it directly onto the virtual hardware and run the machine learning algorithm in simulation. And also the big advantage of these models is that they're provided with very large amounts of simulated memory, so we can run quite large machine learning algorithms and experiment them without having to develop special hardware. So this is a very good route to getting some initial experiments with your machine learning algorithms. Now, when you are creating or going to add a machine learning algorithm to your application, you're going to have to acquire lots of data, train your model and deploy it. So that becomes quite a valuable asset. So you do also need to think how you're going to secure the machine learning model on your device, particularly if it's on a connected IoT device. So it's worth looking at the ARM platform security architecture. So this has a block of firmware called trusted firmware that's designed to run in a secure partition. So here we're creating a partition between our non-secure application code and then a secure region of protected code where we can run various services. So here we've got things like cryptography and storage services, but we can install our inference, our machine learning algorithm, as a service within the platform security architecture, so that it's protected within the trust zone secure environment. So again, it's at the beginning of a project, you need to consider how you're going to deploy your device, how your algorithm, and also how you're going to protect it over time as well. So in terms of the Cortex-M processors, from the Cortex-M4 and upwards, we have hardware floating point, and we also have the SIMD instructions, which can do multiple single instruction, multiple data, so they can process integer values very quickly in a sort of pipeline. So really the Cortex-M4 is probably the minimal Cortex-M processor that you'd use for machine learning. Moving on to ARMv8, we have Cortex-M33, which again has floating point and the SIMD instructions, but additionally has the trust zone peripheral, so we can implement our security model. And now just emerging, starting to come out as real devices, we have Cortex-M55, which also has the helium vector extension. So this is a big boost, both integer and floating point performance. So it gives about a 5 times maths performance over Cortex-M4. So again, M55 will be an ideal device for running machine learning algorithms. Alongside these processors, there is the separate co-processor, the Ethos NPU. So it's either Ethos U55 or 65. So this provides up to 256 multiply accumulate units. So this provides an incredible boost for machine learning algorithms, about 480 times over Cortex-M4. So as I say, these are just about emerging onto the market, and they will make running complex and large machine learning algorithms practical on small microcontrollers. Okay, so to start to look at machine learning algorithms, within a neural net, the smallest element is a perceptron. So this is a simplified model of a biological neuron. So on the left, we have inputs. These may be pixels from an image or elements in a time series. Plus at the top, there's a bias value. And these are all connected to an accumulator that sums up values. And we also then have a set of input weights that we can adjust to change the importance of each input value. We can then have an analog output, which we might use directly in the case of regression, i.e. predicting next value in a series, or we can add an output function, an activation function that provides a nonlinear output. So this helps us train a neural net to classify groups of data that are need to have a nonlinear manifold between them. So then to create a neural net, we need to arrange our perceptrons as a series of layers. So each of the dot here is a perceptron, and all of the outputs are connected to all of the inputs in the next layer. And we can add more and more layers, hence the term deep learning. So all of the inputs to each layer will have a weight. So there's a lot of little values that need adjusting. So to begin with, we have a general purpose algorithm, so a set of layers, and then we can customize it to classify different objects by adjusting all of the weights within each of the different layers. And in terms of the output, we can have a single perceptron output. Again, if we're predicting a value, we just have an analog output. We can add an activation function if we want to do binary classification. If we're doing multi-class classification, we have a slightly different output layer called a Softmax layer. So here, the Softmax layer takes the output from the last fully connected layer, and then it will give a probability output for each class of object that we're trying to identify. So here at the top, it might be 70% cat, 20% dog, 1% racing car. And then once we do the inference, we can look at the outputs and we can make a decision on what object has been recognized. Now, to develop our model, we have a fairly well trod methodology. That first of all, we start by defining the model. We then have to train the model, and that's adjust all of the weights in the neural net until they give us the correct outputs for the input that we're providing. We then test the model to make sure that it matches the accuracy that we need. And then to get it down to the microcontroller, we quantize it to reduce the memory requirement. Again, retest to validate that the model is still accurate enough. And then we can export it. As I mentioned before, this will be as a header file that we add to our project. Now, in terms of training, we do what's called supervised learning. So this has to have labeled data. And this can be a problem for a lot of projects, that we have to acquire the sufficient amount of data, and then we have to label it to say what it is, whether it's a cat, a dog, or whatever in the term of images. So then what we do is we apply an item of our data to the neural network, and we apply the output label, and we measure the difference between the output of a neural net and the applied label. And this gives us an error value that we can feed back to adjust all of the weights in the neural net to try and minimize the error. And that summing value is a loss function. And we have different types of loss functions depending on the type of classification that we're doing. So what we're in effect trying to do is adjust all of our weights so that they minimize the error. We're navigating to the kind of the bottom of the feature landscape until we get a minimum error so that we recognize our particular algorithm. And the training algorithm that we commonly use is called stochastic gradient descent. So again, we're really looking at the gradients, and when those gradients go to 0, we've reached the minima and we've trained our network. So we're applying all of our different images with their labels. We're manipulating the weights for each image until we zero everything out. And then we go round that whole process again and again and again. So we're going through and using the training data over and over until we get a good fit for that model. To do this, as I've mentioned, we need to have a large data set that's labeled. And when you're beginning, obviously we don't have that or have much experience with it. So there are a few data sets that are commonly used and are good to start experimenting with. First of all, there's the MNIST data set, which gives us handwritten labels from 0 up to 9. There's also another data set called MNIST fashion that gives us 10 items of clothing as black and white grayscale images. So these are on a plain background, so they're quite good for early object or image classification. A more complex data set is called CIFAR 10. So these are color images on various different backgrounds. So again, these are more difficult to classify. But these three data sets are commonly used for early experiments and can be directly downloaded into a Jupyter notebook. So when we are creating our model, just to have a look at a little bit what the code looks like. So at the top here, we're defining our model. So first of all, this is a sequential model, so that each of the layers that we're defining will be executed one after the other. So the inputs at the top, so we're inputting an image which is 28 by 28 pixels. We then have a layer of 100 perceptrons with a ReLU activation function. We then have another layer with 200, and then finally we have a softmax layer at the output. So again, creating these models a bit like Lego, we're just sort of sticking layers together and experimenting with values. We then have to compile that model. So this is, we define the loss function and the optimizer for the gradient descent algorithm. So in this case, we're using one called Adam, which detects local minima, so we don't get stuck in a side valley. And then we can also just say what metrics we want to display. So typically for classification, we want to look at the accuracy of the model. And then finally, we can train the model. So we can just start it training. So we provide the image data, the image labels, and the number of epochs, so the number of times we are going to run through all of that training data. The model will then be trained on that data, but we want to check that it generalizes to other data. So we provide a validation data as well. So we train on a large block of data, then validate against a smaller block of data. And that will give us a validation accuracy as well. Once we have a trained network, we can then evaluate it and providing some test data that's not been seen by the model to date. So this gives us a realistic idea how it will perform in the real world. And then we can also call model predict, which will do a prediction for an individual item of data in its label. So here we've got the output from the softmax layer, where we have a 1. This is saying this is the object that we've detected and classified. So to take that down onto the microcontroller, as I mentioned before, we quantize it. We can then export it as a header file. And we need then to add the TensorFlow Lite micro interpreter. So this is installed on the microcontroller. It's available as a software pack, so we can download it and install it into the Microvision toolchain. Then within the runtime environment, we can simply add it and we can decide whether we want to use the Ethos neural net as to run the model as pure software on our microcontroller. Or we can select the Ethos driver if we have the neural processing unit available. So this adds the C++ library to the model, and then we can run an inference, provide data, and then run an inference on our microcontroller. The major memory allocation is for a tensor arena. So here we have to define a large array that's then used by the interpreter. And this can be anything from a few tens of K up to tens of megabytes, depending on the model that we've defined. Also available as a pack is an ML evaluation kit that's available from ARM. So again, this adds some high-level C++ code for common use cases. So we have a generic inference. We can also have some anomaly detection, various vision classification, and also audio classification as well. So again, these are very, very useful bits of C++ code that do a lot of the low-level work for us. Also included in this kit are a set of complex pre-trained models as well. There's one called YOLO, you only look once, and this is for object detection. So again, this provides a very fast and quite state-of-the-art object detection algorithm, and that will run at video frame rate, so you can do still or video images. There's also another model called MicroNet that was developed by ARM, and this provides very high accuracy for keyword spotting as well, and can also be used for anomaly detection. Both of those models rely on another type of algorithm that we can run on the microcontroller called a convolutional neural net. So at the bottom, we have our artificial neural net, so our dense, fully connected layer, and then our output softmax layer. But above that, we have a set of DSP type processing stages. So we have a set of convolution filters, and these will run a convolution kernel across the image. And typically we have a bank of filters, so 16, 32 filters. And these, the results of these are then stored into a pooling layer, which is used to reduce the dimensionality of the image. So as we move down the convolutional layers, the overall size of the image map or feature map gets smaller and smaller until we can put it into our fully connected layer. So a convolutional neural net is really state-of-the-art for image recognition, and it'll blow an artificial neural net out of the water. It also scales very well, so it can handle larger images, and it because we're using a convolutional filter, the detection of the image is done over the whole of the detection of features rather is done throughout all of the image. So this makes it what's called translation invariant. So if we're looking for a particular object, an artificial neural net will be trained to recognize that object, but in a certain location on the screen, whereas a convolutional neural net doesn't care. It scans the whole image and will find that object wherever it is. So it has some distinct advantages over a neural net. Also, each of those layers correspond to a sort of spatial hierarchy. So, for example, if you're looking at the image of a cat, the upper layers will detect the cat, and then the lower layers will detect features within the cat, so its eyes, its nose, etc. So this is a bit strange to begin with, but very useful when you start to understand how it's working. And also the pooling layer is doing this form of dimensional reduction. So as we go through the convolution and pooling layers, the feature map of each image is getting smaller and smaller. And we can do this either through looking at a block of pixels and taking the maximum value, so max pooling, or we average the block of pixels to 1 pixel value. Alongside using a convolutional neural net to detect features in images, we can also use it for time series data as well. So this is generally over a short block of time series data. There are other methods for arbitrary length data, such as recurrent neural nets. So basically, we take the time series data and we pre-process it into a spectrogram using an algorithm called a Mel frequency cepstral coefficient. So this takes our input audio data, we run it through the MFCC, and we get a spectrogram picture of the word or the sounds that we're looking at. This picture can then be interpreted by a trained convolutional neural net to give us a output to say on, off, up or down, etc. So this is the method used typically for keyword spotting. And using the MicroNet model, you get an accuracy of about 96–97%. And running this within the software simulator, in pure software, the inference, so not the MFCC, but just the MicroNet inference, took just over 800 microseconds. But using the Ethos NPU, that went down to 12 microseconds, and that's such a massive gain. I still have doubts I've done it right, but that's what the timing within the model said. So it's just incredibly fast compared to just running it within the Cortex processor. However, the MicroNet model is quite large. So again, that's taking just below 70 megabytes of data. So again, you need a device with a lot of external SRAM. Other algorithms, you can get a lower precision on keyword spotting, but with just tens of Ks of data. So again, it depends what you really need and what you're trying to do. So as I mentioned, the Ethos NPU is just about coming available in small microcontrollers, and it adds this massive performance boost to our machine learning algorithm. So effectively, it sits alongside any of the Cortex-M processors, not just the newer ARMv8, but any of the original ARMv7. And it's scalable, but it can provide up to 256 multiply accumulate units. And this gives us this massive performance boost of up to 480 times performance boost. And again, although there's very limited hardware at the moment, you can experiment with it within the virtual hardware models. And in our more detailed webinars, we'll provide examples that will run on the simulation model. And at the moment, this is free to download, so you can download the simulation model and run the code on it. There's also a new manufacturer called Aleph Semiconductor, who produced a range of Cortex-M55 based microcontrollers, which either are single or dual Cortex-M55 with either single or dual NPU on the device as well. So again, this is going to be an incredible platform for machine learning algorithms. So to use Ethos, fortunately, it's very much like a black box. So we can go through our original methodology, get down to quantizing the model, and then we can use a compiler called Vela that's available from ARM. So you can just install that into Python, and then we can compile our model to use Ethos. And then we just export it again as a header file and add that to our project and use the Ethos driver to download our inference model onto the device and run inference on the device as well. So switching to use Ethos is very, very straightforward and very easy. Thank goodness. So at the moment, we can run all of that as a simulation model. So within MDK, we can select the ARM models, and then we can select the Corestone SSE 300. So that gives us Cortex-M55 and Ethos U55. Planned a bit later this year, the mod will also be able to accept streaming interfaces for audio and video. So this means that we'll be able to have a complete experimental design environment in simulation on our PC. So these models are included with the MDK Pro. The fixed virtual platform models can be downloaded and used for free. The virtual hardware models are available as a 1-year license as well. Now, as mentioned earlier, one of the big bottlenecks in using machine learning on a small microcontroller is that we need to have not just data, but we need to have labeled data as well. And that can be quite difficult to acquire, and then you spend ages having to label it. So one approach that minimizes the use of data is to use an approach called transfer learning. So here we can take an existing pre-trained model, and there are quite a number that are published as part of TensorFlow. And we can take the bottom layers of the model and freeze all of the training weights within them. And then we can add a custom header layer, and then we can train that for our particular task. So we could take a general purpose audio model, and then we can train it to recognize various keywords, for example. So this takes a lot less data and also reduces the training time as well. So transfer learning is quite a good way to take a well-trained pre-existing model and then adapt it and repurpose it to our needs. Similarly, we can use another approach called an autoencoder. So here we have an input where we put our input data, and this is then encoded into a neural net or a convolutional neural net. We then decode it back to the original. So for example, we put in the picture of a cat and we get an output as a picture of a cat. So our input data becomes the training label for our data as well. But what we're effectively doing is training the encoder with the features of our data. So this means that we can use unlabeled data because the input is the output, and we train it on the basic features that are going to be in our data, and this is called the latent representation. We can then take those encoded layers, and we can then put on our custom output layer, and as in transfer learning, we can then train that output for our particular task. So we have our latent representation that will do the initial feature recognition, and we can then take those features to perform our custom classification. So this requires, again, a much smaller labeled data set, and it also allows us to use unlabeled data for the initial training. So it's quite a good shortcut for our uses. Well, I hope that's been useful today and give you a feel of what's coming. But we'll do a set of 4 webinars that will first give you an introduction to artificial neural nets, tools and building a basic neural net. Second session, we'll have a look at how to build a artificial neural net for classification, and also how to optimize it to run on a small microcontroller. In the third session, we'll have a look at convolutional neural nets, both for image and time series classification, and also how to optimize the interpreter, the TensorFlow Lite interpreter as well. And then finally, we'll round off with a look at how to use pre-trained models and autoencoders. And we'll also have a look at running code on the Ethos coprocessor as well. So I hope you can join us for that. Thank you very much.